And today I'll be talking about radioactive decay of uranium-235. U-235 undergoes first-order reaction kinetics, so we can use the first-order reaction model to model this problem that I've been given. So after 10,000 years, 99.999015114%, almost all of it, of a sample of U-235 remains. So we've lost, it's a very small portion, but in some way we measured it, of this uranium, and we want to figure out what the half-life of uranium is. How long will it take for half of the sample to be gone, for 50% of it to remain? So we can use our first-order reaction equations, and that says that the natural log of n time t is equal to the natural log of initial n, where n is the number of particles. It's important to note here that when you're doing this for radioactivity, you're going to use n, which is the count of particles. When you're doing this for chemistry, this is going to be a concentration, and you'll use these brackets to denote molarity or molality, whichever you're using. So let's finish writing this equation. This is minus kT. So here's the integrated form of the first order reaction equation, and we can rearrange it as such. Natural log of n at time t over n at initial time is equal to negative kT. It's just using your log rules. And then this k, we know something about it because we know that k is equal to the natural log of 2 over T1/2 in a first order reaction system. So this T1/2 is what we're looking for right here, that half-life. So let's go ahead and plug this k in over here. And we get the negative natural log of 2 times t over T1/2. Well, excellent. So how many particles did we have? The number at time t and number initially. Well, the important thing here is we don't actually have to know the number. We just need to know the ratio of one to the other. And we're given a percent out of 100. So that means that the natural log of 99.999001514, and I will cut it off here so I don't have to write the rest of those decimals, but you should preserve your sig figs for a problem like this. Over 100% is the initial amount, and that's going to be equal to the negative natural log of 2, which is a known quantity, times t, which we know as 10,000 years. We're given that number, over T1/2. Well, now here we have an equation with only one unknown. So we should be able to simply go through and solve for this T1/2. And if we do that, we're going to find that T1/2 is equal to about 703 million years. Quite a while. Obviously, this isn't the method that people used originally to figure out the half-life of uranium-235, as it took 10,000 years to lose less than a 10,000th of a percent of the sample. No one's going to wait around that long. It's inconvenient. There are other methods of doing it. But this illustrates the equations that you can use. For more information, you can come to my workshops, 6 to 7 p.m. on Wednesdays in Brown West 210, or my office hours 2 to 4 p.m. Mondays and Wednesdays in Casa.